Okay, check what this undergrad wrote. Given a 2 Hz bandwagon, the nice-squirrel frequency must be 1 Hz to avoid aliening of the Fourier transformer.
I take it that is wrong?
It's downright pathetic. 1 Hz. Come on.
Bandwagon, NyQuil, Fourier. The upsetting part was the sampling frequency, so we will get it right with this presentation. Let's sample the everlasting signal x of t with a train of impulses. The signal is band limited in frequency. The Fourier transform of a train of impulses in time, it is also another train of impulses. Note that they are separated by 2 pi t1, where t1 is the sampling period that we're using for sampling x of t. The multiplication of this train of impulses with the signal x of t equates to a convolution in frequency. As there is no overlapping of the replicas of x of omega in the convolution, we can see that a low-pass filter can reconstruct back the original x of omega. If we sample at a slower sampling rate t2 seconds, we can see that in frequency we will have the overlapping of these x of omega replicas. The minimum sampling rate will be when these replicas do not overlap. The minimum frequency that we can use is given by the Nyquist rate, which is equal to 2 times the maximum frequency of our original signal. We have assumed that sampling involves the multiplication of those impulses with the original signal. In the frequency domain, we can see that the Fourier transform of those impulses is actually very simple, is equal to 1. Now, those dots on the left and on the right means that this signal goes from minus infinity to infinity in frequency. That is, it has an infinite bandwidth. So let's say that you would like to record these impulses, so you grab your oscilloscope 200 MHz bandwidth that you actually paid not much for it. And as you can imagine, being this signal of infinite bandwidth, that oscilloscope won't do the job. But you are a successful engineer, you have a much better oscilloscope that you paid way more for it, and you'll give it a try. It still won't do the job. We cannot work with these Dirac impulses. They're not practical, and this is why we're going to talk about practical sampling. A more feasible impulse that we can use at home will look like the ones in green. This train of non-ideal pulses, which are periodic and everlasting, has a Fourier series decomposition. Multiplication of x of t with this Fourier series decomposition yields the following expression. Taking the Fourier transform of the expression on the right yields for the first term x of omega is 0. So the shape is the same, it's just an attenuation most likely that is happening to the original x of omega. For the last term in frequency, we just have a modulation of x of t. Without losing sleep because of the attenuation, once again a low-pass filter can recover the signal x of t. Then, having samples that we obtain from these weirdly shaped non-ideal sampling pulses, we should be able to obtain a fairly good reconstruction. In time, our ideal low-pass filter looks like a sink, which is going to be convolved with x of n. The addition of those slightly modified sinks will give us a fairly good reconstruction. Remember, we have proved this mathematically, so it has to be true. A DSP system may consist at the beginning of an amplifier and an anti-aliasing filter, but if you think about it, the sensor itself would be band limited. An ultrasound transducer or an antenna doesn't have an infinite bandwidth, so the anti-aliasing filter can be included in the sensor. We can think of the sensor acting like that. Then we take the discrete samples using an analog to digital converter. Once we have these discrete signals, we can use DSP hardware to do, for example, filtering. We might have some other type of inputs from other digital systems, let's say temperature. In the case we need to reconstruct back to the original domain our modified signals, we will be using a digital to analog converter, but maybe the process signals will be used by other digital systems, so in that case we don't need to do the conversion to the analog world. But in the case of processing, for example, audio, we need to send those process digital signals into analog speakers, so we will require a reconstruction filter and maybe an amplifier. Now let's say that we would like to sample that analog signal and that the sampling frequency will be 3 Hz. We know that that sampling frequency is greater than the maximum frequency of that single sinusoid, which is 1.25. that means 3 satisfy the Nyquist rate. So the discrete signal that we obtain is x1 of n. If we sample at a faster frequency rate, in this case 4 Hz, we obtain x2 of n, and we should definitely not have any trouble reconstructing the signal back. If we analyze this signal via the discrete Fourier transform, this is what we obtain for x1 and this is what we obtain for x2. Note that they look quite different, but I assure you that the peak is located at 1.25 Hz in both cases. The explanation of these differences requires us to study the discrete Fourier transform. To add to the differences, we also know that plotting the spectra in decibels and without the log will yield also different shapes. But once again, that frequency at 1.25 remains at the exact location. Another aspect to consider is the duration of the signal that will be analyzed using the DFT, that is how many samples we will be using. The example for this part is a multi-component signal that consists of 3 sinusoids. Note that at a sampling frequency of 2000 Hz, we satisfy the Nyquist rate, as the maximum frequency of x of t is only 500 Hz. Remember, omega is equal to 2 pi f, then the 500 Hz that I mentioned before being the maximum frequency of that multi-component signal. Here is how the magnitude of the DFT looks like, where we took 128 samples. The 250 Hz component appears here. This is the 265 Hz. And the little fellow that has an amplitude of 0.1, which corresponds to the 500 Hz tone, appears way below. If during our data acquisition we only acquired 32 samples, we can see that the 2 closely spaced components are not discernible, as well as the little fellow at 500 Hz. By the time we learn more about the DFT, all these issues will be better understood. Thank you.